that fanfare was warranted. Over the last year, the vector signal transceiver has been one of the most successful products that NI has ever launched, both in its sales volume and also in the diversity of applications that it's been able to address. Everything from next generation communications research to high volume production test of wireless devices. And we see a tremendous opportunity to build on that success to solve even more applications. So to talk to us about the latest innovations in our platform for automated test, please welcome Scott Rust, Ryan Barrett, and Dr. Takao Inoue. Welcome back to Austin, Scott, and back to the NI Week stage.
All right, thanks, Eric. In R&D, we've been very hard at work, and we're proud to announce several new hardware products across the entire LabVIEW Rio architecture. But perhaps the most significant announcement is a new method of programming the BST's FPGA that makes this exciting technology even more accessible to our customers. So we're going to dive right in and show some of this hardware in action. We're going to start with a demo of the BST testing the front end of a modern RF transceiver.
In this system, we have 3 analog ICs provided by Keynote, a leading microwave component manufacturer. We've got a modulator, a variable gain amplifier, and a power amplifier, which are all components you might find in your cell phone or wireless router. First, we're going to test the modulator and variable gain amplifier using an LTE signal, which is the standard behind 4G cellular. So Cal, if you wouldn't mind running the demo. Now, we recently released our second vector signal transceiver, which is perfect for this test because it has the baseband I/O necessary to test the modulator inputs.
All right, we're over 12 times faster than a competitive box instrument right out of the gate.
That's right, we're significantly faster than the competition, making measurements at 64 different test points. But Scott, we're not actually even taking advantage of the open FPGA on the VST.
Okay, hold on a second. Eric just spent a lot of time talking about the great applications we can enable by allowing customers access to the FPGA. How come you're not doing that here?
Well, to understand why, I need to explain a little bit more about our VST software. So far, users have had 2 options for programming their VST. First, we have a completely open software stack that delivers the full flexibility of the LabVIEW Rio architecture and was used in many of the applications that Eric described earlier. But we also have customers that want to port their code from other RF instruments, written using familiar industry-standard instrument drivers, but with a closed FPGA. And inevitably, for the VST, once these customers get up and running, that's when they start asking about customizing that FPGA.
Yeah, and so what's revolutionary about the BST is that its FPGA code is written entirely in LabVIEW. So let's open it up.
Well, I was hoping you'd say that. I'm proud to introduce a revolutionary new feature called Instrument Driver FPGA Extensions. It's really the best of both worlds. You can use our standard instrument drivers just as you normally would, but you can also add your own application-specific tweaks to the FPGA. Furthermore, we have a number of pre-compiled personalities available on NI.com, so you can download them and get started with Instrument Driver FPGA Extensions right away.
And this really is an important new feature capability. It really does provide the benefit and flexibility of an open FPGA, along with the functionality that many of our users expect from standard RF test equipment.
That's right. Instrument Driver FPGA extensions are going to empower the entire community of LabVIEW users to make enhancements to their software design instruments. So let's see what you can do with this technology in your demonstration.
So first, we're going to embed a serial protocol onto the VST FPGA so that we can communicate with our device under test through its digital port. We're also going to embed a hardware-based test sequencer, which tells our VST generator what waveforms to output, the analyzer when to acquire data, and the digital protocol engine when and how to reconfigure the device under test. Now we can execute the entire test sequence from the FPGA much faster than the CPU. And you can think of this as moving control from your test executive down into your instrument hardware. So let's run the demo again with Instrument Driver FPGA Extensions.
All right, it's over 60 times faster. Yeah, that's good. Making it better and better. So moving some of the processing from the host computer down into the FPGA has made a huge difference in this application.
That's right, Scott. Now, in addition to providing these devices for us to test here today, Hittite is also a leading user of this new technology. They're doing a similar kind of duct control on one of their latest mixed-mode ICs and seeing a speed improvement of more than 30 times compared to their traditional rack and stack approach. But back here on stage, we've actually accelerated the VST so much that we're waiting on the CPU to perform the analysis.
And fortunately, we have another technology that can help. Today, I'm proud to announce our first PXI multi-computing product. PXI-MC allows users to easily transfer data between multiple independent systems, either based on PXI or standard PCs.
Yeah, I'm personally excited to see this product hitting the market. I was involved a few years ago as we were defining the standard, and our goal was to overcome some of the bandwidth and latency limitations of Ethernet, but create something that was much easier to integrate than technologies like reflective memory.
That's right. We've got over 15 times more bandwidth, and since this is based on an open industry standard, it's very easy to program, so that gives our customers the flexibility to add advanced processing power to their applications whenever and wherever they need it. So let's see what you can do by adding a high-performance server to your application.
Sure thing. With PXI-MC, we can distribute the load of our analysis over 2 machines, processing our acquired data much faster. And here you can see that hopefully we've reduced our test times even further, now more than 100 times faster than the competition.
That's really a pretty astounding result. It's 2 orders of magnitude faster. I think sometimes at NI we almost get numb to this because we see our customers get order of magnitude performance improvements, almost every day. But it's a good reminder that in customers in production tests, for example, this is incredibly valuable. These customers are saving hundreds of thousands or millions of dollars a year due to performance increases like the one you just saw. I do want to emphasize, though, that the vector signal transceiver isn't only for production test applications. Takao, you've been doing some work for RF design. Why don't you tell us about that?
Sure.